physicists from Switzerland, Germany, and Ukraine have proposed an innovative new data storage medium. The technique is based on specific properties of antiferromagnetic materials that had previously resisted experimental examination. Using nanoscale quantum sensors, an international research team has succeeded in exploring certain previously uncharted physical properties of an antiferromagnetic material. Based on their results, the researchers developed a concept for a new storage medium published in the journal Nature Physics. The project was coordinated by researchers from the Department of Physics and the Swiss Nanoscience Institute at the University of Basel. Antiferromagnets make up 90% of all magnetically ordered materials. Unlike ferromagnets such as iron, in which the magnetic moments of the atoms are oriented parallel to each other, the orientation of the magnetic moments in antiferromagnets alternates between neighboring atoms. As a result of the cancellation of the alternating magnetic moments, antiferromagnetic materials appear non-magnetic and do not generate an external magnetic field. Antiferromagnets hold great promise for exciting applications in data processing, as the orientation of their magnetic moment, in contrast to the ferromagnets used in conventional storage media, cannot be accidentally overwritten by magnetic fields. In recent years, this potential has given rise to the budding research field of antiferromagnetic spintronics, which is the focus of numerous research groups around the world. The research team examined a single crystal of chromium-3 oxide. This single crystal is an almost perfectly ordered system in which the atoms are arranged in a regular crystal lattice with very few defects. We can alter the single crystal in such a way as to create two areas, that is domains, in which the antiferromagnetic order has different orientations. These two domains are separated by a domain wall. To date, experimental examinations of domain walls of this sort in antiferromagnets have only succeeded in isolated cases and with limited detail. Thanks to the high sensitivity and excellent resolution of quantum sensors, the researchers were able to experimentally demonstrate that the domain wall exhibits behavior similar to that of a soap bubble. Like a soap bubble, the domain wall is elastic and has a tendency to minimize its surface energy. Accordingly, its trajectory reflects the crystal's antiferromagnetic material properties and can be predicted with a high degree of precision. The researchers exploit this fact to manipulate the trajectory of the domain wall in a process that holds the key to the proposed new storage medium. To this end, the research team selectively stretches the surface of the crystal at the nanoscale, leaving behind tiny raised scores. These scores then alter the trajectory of the domain wall in the crystal in a controlled manner. The researchers can use the orientation of the raised scores to direct the domain wall to one side of the score or the other. This is the fundamental principle behind the new data storage concept. If the domain wall runs to the right of a raised square, this could represent a value of 1, while having the domain wall to the left could represent a value of 0. Through localized heating with a laser, the trajectory of the domain wall can be repeatedly altered, making the storage medium reusable. Next, the researchers plan to look at whether the domain walls can also be moved by means of electrical fields. This would make antiferromagnets suitable as a storage medium that is faster than conventional ferromagnetic systems while consuming substantially less energy.